Interpol is late to a mind-blowing math hack. Just the facts. It's an episode of the Degrees of Freedom Project, videos on chemical and thermal principles. Definitions and additional details can be found in the web page link in the description. This video discusses the basics of linear interpolation in 1 and 2 dimensions. Before the age of readily available computers, most engineering data were only available as tabulations, usually in handbooks, but sometimes in textbooks or journal articles. Data tables still find extensive use. Here's a portion of a steam table. What would you do if you were looking up a value in the table and needed the specific volume of steam at 9 degrees Celsius? Well, it lies between 8 degrees Celsius and 10 degrees Celsius, where you see the oval here. We could sort of guess that it's someplace between 120.8 and 106.3, so it's probably about 110. Is there a more formal way to go about finding the value? Here we have a blow-up of the part of the table we were just looking at. The most common practice to find the value is to use linear interpolation. You assume that the specific volume of steam between 8 degrees Celsius and 10 degrees Celsius is a linear function of temperature. Is it a linear function? Well, if you think of it as a Taylor series, any function that can be expanded as a Taylor series is linear over a small enough range and nonlinear over a large enough range. The trick is to have the table values spaced closely enough together so that you can treat the data as being linear. What is the linear interpolation formula? Well, I have a poor memory, so the only way that I can remember it is that the slopes are equal. So we have here that the dependent variable y minus y1, which is a table value, divided by the independent variable that we know x minus x1 table value that corresponds to y1 is equal to a table value y2 minus table value y1 divided by the corresponding table values x2 minus x1. Does it matter which table value pair we use as 1 and which we use as 2? No. You can use the points in either order, just make sure that you're consistent. Rearranging the equation and solving for y, which is the value that we're trying to interpolate for, we get the following formula. Y equals y2 minus y1 over x2 minus x1 times x minus x1 plus y1. If you think of it in terms of the equation of the line, we have the slope y2 minus y1 divided by x2 minus x1 times our independent variable x minus x1 plus the intercept y1. Substituting in the temperature and specific volume, we have that v hat is equal to v hat 2 minus v hat 1 over t2 minus t1 times t minus t1 plus v hat 1. Substituting in the numbers, 106.3 minus 120.8 divided by 10 minus 8 times 9 minus 8 plus 120.8 equals 113.6 cubic meters per kilogram. That covers the basics of linear interpolation. We discuss other methods of interpolation in the next video, nonlinear interpolation. They are useful when high precision is needed, especially on a widely spaced table. Now we'll discuss double interpolation. This comes about if you're between values in a two-dimensional table instead of a single-dimensional table. Here, we have part of a steam table. Let's suppose that we need to interpolate temperature of 125 degrees Celsius, which we see is between 100 and 150 degrees Celsius, and a pressure of 0.3 bar, which we see is between 0.1 and 0.5 bar. The specific volume, which we are looking for, is in between all 4 of the values, as you can see in the middle of the table. So what do we do? Well, we use double interpolation. It's called double interpolation, but we actually have to do 3 interpolations. It's called double because you're doing it in 2 dimensions. Let's start by interpolating on the temperature first, then the pressure. In this case, we will interpolate at 0.1 bar between 100 and 150 degrees Celsius at 125 degrees Celsius, getting 18.35. Then, we interpolate at 0.5 bar between 100 and 150 at 125, getting 3.655. Our final interpolation will be in our column of 125 degrees Celsius, and we will interpolate between 0.1 and 0.5 bar, getting 11.003. Obviously, you would round these values to have the same number of sig figs as in the table. We're not rounding here so you can see all the digits from the interpolation. Next, let's interpolate on pressure in the 2 temperature columns, and then we'll do one final interpolation using temperature. First, we interpolate at 100 degrees Celsius between 0.5 bar and 0.1 bar. we end up with 10.31. Then we interpolate at 150 degrees Celsius between 0.1 bar and 0.5 bar to get 11.695. We then interpolate using temperature along the 0.3 pressure row again, using 125 degrees Celsius, and we end up with 11.003 as the final answer. You'll note that the two answers are the same. That's because if you're doing linear interpolation among the four values, it doesn't matter which order you do it in. There's a link to the spreadsheet with these examples that include nonlinear interpolation in the descriptions below. The takeaways from this video are 1. If you have a table of values and you need a value that isn't at one of the table entries, use interpolation. 2. You can rederive the formula if you can remember that slope equals slope. 3. For a table with a single independent variable, use 1D linear interpolation. And 4. For a table with two independent variables, such as temperature and pressure, use 2D interpolation, which actually requires 3 1D interpolations. Thanks for watching! This video is brought to you by the DOFPro team.